So number 14 then from the 2018 SQA Advanced Higher Mathematics of Mechanics, a 5-mark question on, looks like elastic motion. What does it say? A bungee jumper of mass 70 kilograms stands on a bridge which is 40 metres above a river. I'm not drawing that in. The natural length of the bungee cord, so if it was just hanging straight down, would be 10 metres. It's got a modulus of elasticity of 1,000 newtons. Now that can have a variety of forms. You might see it as newtons per square metre. That's the original Young's modulus. If that were the case, you'd have to know the dimensions of this cord, its cross-sectional area and its length. You might see it as newtons per metre. That's what's known as the spring constant. If that was the case, that means all the dimensions have been taken care of, the cross-sectional area and the length, so all you have to do is multiply it by the length of the extension to get the force. Or you might see it just as newtons, as in this case, which means the cross-sectional area has been taken care of, but the length hasn't yet been included. So for this one, if you're wanting to work out the force that's going to be caused by this extension, I should have put that in, if it's extended by an extra amount d, that force will be, yes, it'll be the 1,000 newtons, but times the d divided by the original length. That makes that unitless, so it still stays as newtons. Anyway, with that diversion over, and this one here, there's several ways to answer this question about how high above the river you would end up. By far the simplest is just to use conservation of energy. At the start, this 70 kilograms is this height above this datum here, the final position, so you can work out the potential energy that's available. What happens in between is there's all sorts of combinations of transfers to kinetic energy and some of the elastic energy, but by the time you get to the bottom and it stops, all that potential energy has been transferred, into this stretched cord, so it's all become the elastic energy. Well, one of the first things would be, you know how to work out the potential energy. I'll put it down anyway. That potential energy, which is the initial energy at the start, is just mgh. Now, since it's above the datum, that's going to be mg times L plus d. If I'm calling that, I've still put an L in there, L plus d. Now, the final energy will be the energy stored in the elastic cord when it's fully stretched. Well, the way you could work that out is by how much work would you have to do to stretch it, because that work then is what's been put in as its internal energy. Well, that work would be, that internal energy would be, you'd have to add up the force times the distance, but it's variable, so it'll be the integral of f dx. And the total work done would be from when it was not stretched at all till it was stretched to a distance d. So that's the integral from 0 to d of, and if you put in the force with a length of 10, that's 100. It would be 100x, I didn't mean to put a d there, I meant to put the general case of an x, dx. So working that out, that would be, add 1 to the power divided by the power, that would be 50x evaluated from 0 to d, 50x squared, so that's 50d squared. But you know that for a spring anyway, you should be used to that one. In a spring, the energy stored in a spring, you know, is a half kx squared if x is the extension. Because remember, this 100 here came from that modulus divided by L. And when you divide it by L, you've got the newtons per metre, and of course that's the one that's equivalent to the spring constant. Right, so that's simply 50d squared. Now, I've probably already accumulated a couple of marks here. I should have been looking to see what was happening. There's 1 mark for getting for the elastic energy. There's another mark for getting the potential energy and equating it to that. So that's what we'll have to do. We'll just have to do that. These two should be the same. So I'll just put it the other way around. So 50d squared, I'm just putting this up there in this way. The potential energy gets transferred into elastic energy. So 50d squared will be, I'll put the figures in now, 70 times 9.8 times 10 plus d. Doing that gets the mark. Now what you've got is a quadratic equation to solve. So not an awful lot to this question if you do it this way. Energy at the start, energy at the finish. Potential energy, elastic energy. And if you remembered that a half kx squared, you'd have got that straight away. Now, d squared would be, I'm just bringing it all across now. Now I might as well calculate these parts. So for this one here, because that's going to go first, bringing it across will be minus 13.72d. Now that is just going to be 10 times that one, so minus 137.2. So there's the quadratic. So solving that is just a case of using the quadratic formula. So the negative of b, 13.72, plus or minus the square root over 2 times a, which is just 2. So that's 13.72 squared minus, but that's a negative, so plus 4 times the 1 just, so 4 times 137.2. Pop that into your calculator. I think we'll do the plus 1 first. So d is going to be, if you pop that in, you get 20.434 and so on, so I'll just call that 20.43 metres. Or, because there's going to be 2 answers, now with the minus 1, I just need to take that 13 away, minus 13.72, and that will give me a negative, because it's the subtraction is the other way around, 6.71 metres, or 6174. Which means d is going to be 20.43 metres, since I'm only interested in the d that extends beyond 0. Did you notice that wee bit of just not doing it again? You could just have changed the plus to minus, but simply taking the difference between them. That's because the sum of those values must be the 13.72, just because the denominator is 2 in this case. And the average of these values is their total divided by 2. So if you subtract the 20 from the 13, you'll get the other one. The other thing here, because it refers to this question, because it's going down above, that mid value, ignoring the plus or minus, that 13.72, if you divide that by 2, you're going to get 6.86. Now that 6.86 must be the extension d that would happen in the equilibrium position, because these oscillations, see that above and below, these oscillations are going above and below a certain point, and that would be the 6.86. Anyway, final part then, so what's the height above the river? Well, it was 40 below, so just take away the distances you know. The static length of the cord was 10 metres. It got stretched by a further 20, that's quite a stretch. So that subtracting that away from that is going to be, well, that's 30 away from it leaves 10, so that'll just be 9.57 metres. And I got carried away, not putting in the marks were all over the place. So obviously there was going to be a mark for forming the quadratic equation, which is just that one there, I suppose, just tidying it up. There was a mark for going through the solution to it. And there was a mark for selecting the appropriate answer, which was this one, the reason, and calculating the height. Now another way of doing it, but a longer way, is simply to realise that this models as a spring, and that if you extend it beyond its natural extension, it's going to undergo simple harmonic motion. So when this bungee jumper comes down on this, there would be a natural extension if you were held static. If you were to jump down and then just hung about for an hour, because with that extension it would take ages to settle down. Wherever it settled down, that would be the equilibrium extension, I'll just call that part delta. And then if you go beyond that equilibrium extension, you've created an unbalanced force, which would then create simple harmonic motion, so long as you didn't go beyond the unstretched length. Because that's where the model breaks down, because it's not a spring, it's a cord, so it can't provide any compressive force. It'd only be a partial simple harmonic motion. It'd be simple harmonic motion the way down, and as soon as it's got to its natural length, this cord can't do any more, you're under just normal projectile motion with gravity. Then you're back to the cord again. But you're only interested in the part down anyway, so you can use simple harmonic motion just in that initial part. Well, if you're modelling a simple harmonic motion, I'll need to know this natural extension length, because that's the part that it's going to oscillate about. And that's where this modulus will come in here, because I'll need the force on it, so I'll have to model it. So the model would be this. On the point, there's going to be a force up the way, which will be the tension in the cord. There'll be a force down the way, which will be the weight of the bungee jumper. And if you're in equilibrium, those two will match. Now the tension in the cord is given by that Hooke's law equation. That tension will be that 1,000 newtons times the extension I'm calling D, but remember it'll have to be divided by, because that doesn't include a length, and it'll have to be divided by 10. Normally the 10 would be over here instead, so it'd be a proper spring constant. So that's going to be 100 delta. The weight, of course, is just the 70g, so you can form this equation then. So probably don't need to write all this down, because it's got quite a few stages in it anyway, but there's some of the forces in the x, and of course we're calling that the direction for x this time, since it's just got the one direction here. And some of the forces in what we're calling x here, because that's the way x is getting measured, is going to be mg minus t, and if it's static, it's held steady. So t is going to equal mg, which is an awful lot of writing for almost nothing, isn't it? So 100 delta will be 70, we'll just leave it as g, 70g, so delta will be 0.7 g. Now if you wanted that as a figure, you could just multiply that by 9.8, and you get, there's that 6.86 you had the first time round for that middle value in the quadratic equation. Now getting either of those is worth a mark, because that's relevant to the simple harmonic motion. But now you need to describe this properly then. What happens if you go beyond that extension then? What's the sum of the forces now? So that was for equilibrium. What's the standard one? Well, this time, this is for x now, mg minus t will not be equal to 0. There'll be an unbalanced force up the way, which will be equal to ma. So if I put that together, 70g minus, now this time the tension will be, same as before, 100 times the distance, but it'll be 100 times, I shouldn't have put that bracket at the front, that distance x plus the extension. That's what's going to equal ma. Now in this, if you were to multiply the brackets, that 100 delta was just the 70g, so it knocks out that term, so you're just left with this. I should have put that m as a 70. ma equals negative 100x. Or in particular, if you rewrite that as x double dot, remember that m is the 70, it's negative 100 upon 70x, which is simple harmonic motion. The acceleration is proportional to the displacement and directed towards the centre of equilibrium. Now, I don't know if you actually needed to go through all that, because if you said you were modelling it as a spring, you could just assume that you had the same situation as a spring, because the spring's the common one, and in a spring you've got x equals negative k. The acceleration is negative kx, where k is the spring constant, because that's of course, upon m. Well, that's the spring constant. But anyway, since that's simple harmonic motion, that means that omega squared is equal to this, is equal to 100 upon 70. See, there's only one mark for all of that, as far as I can see. The mark was actually for omega as the square root, and so on, and I should have simplified that down. What was naughty? But I know I'm going to use omega squared later, in that form. It's quite a lengthy method, this. So essentially all we've done to begin with is just to say, if you modelled that as a spring, what you would have would be an equilibrium position here, and a frequency of the square root of that. The only thing missing then is what's the amplitude, and it's this amplitude you want to know, because that amplitude would be what takes you down to the maximum depth there. You'll have to get rid of all of this bit. So now you know it's simple harmonic motion. You can write down the equation for simple harmonic motion, either x equals, but the better one would be to put the v1 in. V squared equals omega squared a squared minus x squared. That's just by squaring it, of course. Then you could use this to find A, which would be the maximum distance below the equilibrium point. But in order to do that, you'll need a value of V and X, and that's where you can use this initial drop, because before that starts to stretch, you're falling under gravity. So what speed would you get to at this point? And the speed at that point, and you know the distance from the equilibrium position already at that point, will let you work out A, because you also know omega. So falling down under gravity, I'll be using this. V squared equals u squared plus 2as. So you're starting at 0, and it is a plus because you're talking about going down the way, that's the direction. Plus 2 times 9.8 times 10. So V should equal,
what, a calculator?
Just doing the square root in one go, a very nice 14 metres per second.
Of course it is, it's
So
196.
V equals that
Two videos.
when x equals the displacement, which is, but of course this is it before the equilibrium position, negative 6.86. You can pop it into that and get A. So putting it back into the first equation again, we've got this. Let's call that 1. So in 1, we've got 14 squared equals, now omega squared was 10 upon 7. A squared I don't know, but minus, and when you square that it goes positive, so minus 6.86 squared. So if I just do a quick rearrangement, so A is going to be, it's going to be 7 times 14 squared upon 10, let's get rid of them, plus 6.86 squared, and then do the square root of the whole lot. And when you do that and type it in, you get 13.574 and so on. Maybe too many figures there. Now, been lost track of the marks. You're going to get a mark for doing that, for finding A. But you're also getting a mark, of course, for finding this pair of values to feed into the equation. So there's a mark for knowing it was 14 at that distance and then feeding it in to find A. Almost there. Now you can get the height. It's going to be 40 minus, and it was the 10, plus the 6.86, plus the 13.574, which is 9.566, 9.57 metres as before, for the final mark. There's another way which is similar to the simple harmonic motion, only this time I'm not considering any equilibrium position, it's just motion in one go. Or rather, it's motion within this part here once it starts to stretch. So that's the distance x I'm going to use this time for it. It's going to start the same way. How can you describe that motion using the second law to find acceleration? Well, same balance of force. So the force down the way, mg, is minus t is unbalanced, and that will result in an acceleration ma. I'll just put that in. So mg minus, now the tension in the spring will be, again, watch the modulus. So that force is going to be, that 1,000 will have to be multiplied by the distance x, but also divided by the length to keep that bit unitless. Or you could think divide by the length, and there's the spring constant. So it's minus 100x will equal ma, I'll just put it in, will equal ma. Unfortunately the m's don't cancel out, so I'll have to put those in. Now the only difference is, now obviously that's the equation that would lead to simple harmonic motion. The difference being in the simple harmonic motion derivation, that x was made up of two parts, the equilibrium extension and then the distance beyond that, and that would have subtracted away that term. The other difference here is, instead of writing a as x double dot, I'm going to write a in terms of velocity. So for this one, I might as well just put all the figures in now then. So m was 70, I'll still leave the g there, minus 100x equals m is 70. Instead of a, you can use that v dv by dx, because you can see that the equation's got v's and x's in it. So instead of having a dv by dt and integrating those, because there's no t's on this side, you want it in that alternate form. Now it's just a case of separate the variables and integrate. But anyway, writing this first line down, just from equating the forces, or rather finding the unbalanced force and equating it to the accelerated mass times acceleration, then you proceed after that. So, switching side, I think I'll start with this, the v over here, and have that part over there. So I've got v dv equals, I'm going to take the 70 across and divide, because it divides quite nicely into that. So that's just going to be g in that side, but that'll be 100 over 70, which is of course that 10 upon 7, which was that omega squared times x, and that multiplies the dx. Then integrate it up. So integrate both sides. You've got this first order differential equation here, and you'll have this side will integrate up to a half v squared. This side will become, they both just go, that will go up to x, and that will go up to x squared, but it'll be divided by 2, so it'll be 5 upon 7 x squared, but then there'll be a constant. Now, separating them and integrating, that gets a mark. How am I going to find that constant? Well, here you're back to that same situation again. You get the constant if you know a pairing, a pair of v and x. Well, that's where the other mark came in. We did that already. You knew that v was 14 meters per second at the bottom of those 10 meters. So in this case, that's when x, remember, x is the distance measured from there. So x is 0 in this case. So if you put that in, you've got a half of 14 squared is going to be, now that's 0 and that's 0, so that'll just be c, which means c is going to be a half of that, which is 196 halved, which is 98.
There you go.
Now there was a mark for getting that pairing there and finding the constant. Now you can put it all back then, and you've got this, a half v squared equals, I'll just leave it as gx minus 5/7 of x squared plus 98. So what use is that, do you say? Well, now you can find x, you can find this extension to the bottom. It's fully stretched when the velocity v comes to 0. So maximum x means v is 0. So I've got this equation equals to 0. Now you could take the two across, but it makes no difference because they're all going to get that factor. So it's simply this then, I put them in order, I'll write them over there. So you've got 5/7 of x squared minus 9.8x minus 9.8 should equal, whoops, that was a 98, should equal 0. Do I still like that 5.7? I'm just going to rewrite that again, just by taking that across. So that's 13.72.
Not again, it's 10
And that's
times it.
137.2. And that was an x.
Oh,
And you should recognise that as exactly the same equation that you had the first time. So it's no surprise when you put it in, I'm just going to short circuit it. You get exactly the same answers, which is 20.43 or negative 6.71, which means it has to be this one. There's a mark for doing that. And then finally you put it back in the same as you did before. So h is going to be 40 minus the 10 plus obviously the positive one, 20.43. And when you take that away, you get the 9.57 meters for the last mark.
Thank goodness that's over.